Hi gentlemen, these will be your notes for Unit 1, Day 1 for Calc 1. If you would like to see the warm-up review problem or any of the homework or test questions we went over in class today, just look at the finished notes. So today we're going to start with discussing average rate of change versus instantaneous rate of change, and that'll lead us into a discussion about what limits are. So we'll look at limits on a graph, we'll look at them on a table, and we'll look at how to evaluate limits algebraically. So let's start with the average rate of change. I think we covered this in our pre-calculus notes, but average rate of change is just another way of saying finding the slope between 2 points. And so our slope is the change in the y values over the change in the x values, or if you remember your slope formula, it's y2 minus y1 over x2 minus x1. But today we're going to talk about it in terms of function notation. So if we want to find the average rate of change of f of x on the interval from a to b, and remember that's from x equals a to x equals b, what we would need to do is find the change in the y values. Well, to find the y values, you would plug in b and you would plug in a. So that would be f at b minus f at a. And that would be the change in the y values over the change in the x values would be b minus a. So this is your change in your y over your change in your x in function form. This is going to be a very common formula in our class, and that's how we can find average rate of change. So this is the formula for average rate of change. F at b minus f at a over b minus a. So for instance, if we wanted to do this and we were given the formula f of x equals x squared minus 4, and we want to find the average rate of change in between negative 1 and 3, well, we could do this both visually and algebraically. Visually, this would be the happy parabola that moved down 4, and I know it has x-intercepts at 2 and negative 2, and so it would be this parabola right here. Well, if I wanted to find the average rate of change between negative 1 and 3, I would find f at 3, and then I would subtract f at negative 1 over 3 minus negative 1. Well, f at 3, if I plug 3 into that formula, I would get 5, or 3, 1, 2, 3, 4, 5. So it would be this point right there. So this is the point 3, 5. And then I would subtract f at negative 1. Well, if I plugged negative 1 into that, I would get 1 minus 4, which is negative 3. So at negative 1, I'm at negative 3. So it's that point right there. So this is the point, negative 1, negative 3. The average rate of change would be the slope that connects those 2 points. So that would be like the slope of the secant line. So remember we talked about this, the slope of a secant line goes through the graph twice, just like it would on a circle. So the slope of the secant line is going to be your average rate of change. And so this is going to be 5 minus negative 3 over 3 minus negative 1, which would be 8 over 4. And so the slope of that line should be 2, up 2 over 1, if I did all of that right. So that's average rate of change, the f at b minus f at a over b minus a. Instantaneous rate of change, if we want to do that exact same thing, so if we have the same function, f of x equals x squared minus 4, the instantaneous rate of change would be, instead of finding the slope between 2 points, we want to find the slope at exactly 1 point. So if I wanted to know at f at 1, what's the slope? So f at 1 would be right here. And basically what I'm going to do this time is I want to find the slope of the tangent line. So a tangent line only intersects your picture at 1 point. So it lays on the picture. It doesn't really go through it at 2 points. So f at 1, if I plugged 1 into this, I would get negative 3. Well, it's impossible to find slope if you only have 1 point. So what we're going to do is we're going to choose a point that is so close to our original point that they're basically on top of each other. So if I chose x equals 1 as my first x value, then I want x equals 1.000000, as close as I can get to 1 to be my second point. And then if I find the average rate of change, I'm going to have 2 points that are so close to each other that it'll basically be an instantaneous rate of change. So I would find f at 1.00000001 minus f at 1 over 1.000001 minus 1. And that's how we're going to find instantaneous rate of change for right now. We're going to learn how to find it more accurately and precisely using derivatives later on. So if we looked at this using real world examples, to find the average speed, so that's average rate of change during the first 3 seconds, you would find the f at b minus f at a over b minus a on the interval 0 to 3. So we would find f at 3 minus f at 0 over 3 minus 0. So in this case, my f of x is 16t squared. So if I plugged in 3, I would get 16 times 3 squared is 9, minus if I plug in 0, I get 0, then over 3. 9 over 3 is 3, 16 times 3 is 48. So this would be 48, and then we are in seconds, and it's falling in feet. So it'll be feet per second. And then if we wanted to find it on the first 4 seconds, you would go between 0 and 4. If you wanted to find the speed at exactly 3 seconds, so remember, we want to find a point that's really, really close to 3 seconds. So we could do like 3.0000001, and then we would find f at 3.00001 minus f at 3 over 3.00001 minus 3. So you guys can look at our finished notes from class today to see how we did those problems. So a limit is kind of like if you wanted to think about the biggest number that's less than 1. So if you had 1 on a number line, so here's 0. If we had 1 on a number line, what's the biggest number that's right next to 1? So what's the number that's closest to 1 but's less than 1? Well, we could do 0.9. But could I get closer? Yeah, I could do 0.99. Could I get even closer? Sure, 0.999. I could keep going on and on and on and just keep adding 9s, but I would never get as close to 1 as I could possibly think. So getting to 1 would be like a limit of 1. I can get so close to 1 but not equal 1 by just continuously adding 9s. So that's kind of like what limits are going to be like. So what is a limit? So if we were to just sketch a graph, it doesn't have to be anything special. This could just be my graph. A limit is what the height of a graph is as the x values get close to a given number. So it's what the height of the graph is going to be, or what it approaches as your x values get close to a given number. So what limit notation looks like is we write LIM for limit, and then we would say x is approaching, and we can just do like a given value. So we could do a given value of 0. And so we want to know what's the height of the graph as our x values get really, really close to 0. So what's the y value of my graph going to be as x gets really, really close to 0? So it doesn't have to be what the y value is or is close to. So it doesn't have to exactly equal that. It's what it approaches as x approaches 0. So it's what the height of the graph is or is close to as the x values get close to a given number. So as my x values are getting closer, closer to 0, so I'm getting closer and closer this way, what's the height of the graph getting closer to? Well, my height of my graph is exactly right there. So the height of the graph is at -1, -2, -3, -4, -5. So the height of the graph is getting closer and closer to -5 as my x values are getting closer and closer to 0. Well, what's my limit going to be as my x values are getting closer and closer to -4? Well, as I'm getting closer and closer to -4, so my x values are getting closer and closer to -4, the height of my graph is getting closer and closer and closer to that hole. And I know that the height doesn't actually exist at the hole, but that's what my y values are getting closer and closer and closer to. So 1, 2, 3, 4, 5, 6. They're getting closer and closer and closer to a height of 6. So that's going to be the limit of my graph. I can also talk about what's happening at the ends of my graph. So what's happening as the x values are getting really, 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 really big. So I'm going all the way out on the right-hand side of my graph, and my x values are getting big. Well, my heights, notice there has a tail here. My heights are going up. So they are getting closer and closer and closer to infinity. So that limit would be infinity. So again, a limit is the y value that your graph is getting closer to as your x values converge at a certain location. So let's look at this example. So what's going to be the limit of my graph as x is getting closer and closer to -5? Well, here's -5 on my x-axis. So as I'm getting closer and closer to -5 on the graph, what's the height of my graph getting closer and closer to? Well, my height of my graph from both sides is getting closer and closer to a height of 2. So that would be the limit. What's going to be my limit at x is -3? Well, here's -3. So from both sides, what's my graph getting closer and closer to? So coming from the right side of my graph, it looks like it's getting closer and closer to a height of 2. Uh-oh, but as I'm coming closer and closer to -3 on the other side, it's this piece of the graph, and those are getting closer and closer to a height of 5. Well, notice that my two heights are approaching different values. From the left side, it's getting closer to a height of 5, and from my right side, it's getting closer to a height of 2. If they're approaching two different heights, the limit does not exist, and so we just put DNE for does not exist. What's the height of the graph getting closer and closer to as my x values are getting closer to 0? Well, here's 0 on my graph, so it looks like on both sides, the height of my graph is getting closer and closer to -1. What about +1? Well, as my graph is getting closer and closer to +1, it looks like on the right side, it's coming towards this height right here, which is +1. And on the left side, it's getting closer and closer to this value right here, which is -6. But again, since those two pieces of the graph aren't approaching the same height, then the limit at 1 does not exist. What about at 4? So at 4, here's 4 right here. On the left side of the graph, the height of the graph is getting closer and closer to 2. But on the left side, or sorry, on the right side of my graph, it's getting closer and closer to a height of 6. So again, since those two heights aren't approaching the same number, then my limit doesn't exist. What about my limit as I'm getting closer and closer to 6? So here's 6. Notice these two pieces are getting closer and closer to the same height, which is a height of 2. And again, it's okay that it's a whole. That's what the height is getting closer and closer to. It doesn't need to equal exactly that. What about at 8? So at 8 on both sides, well, on the left side of 8, it's getting closer and closer to this, but there's no other piece over here. So since it's only approaching 8, the x value of 8 from the left side and not from the right, we say that the limit doesn't exist because it's not approaching both sides. What about at -8? So the same thing, the right-hand side of my graph is getting closer and closer to a height of 5. But on the left-hand side, nothing's happening. I'm not connected over there, so the limit does not exist at -8. If it's just function notation, so what is the function value at -5? It wants to know what is the height at -5. So this needs to be a closed dot. So at -5, is there a closed dot? There is. It's at a height of 2. F at 1. So at 1, here's my closed dot at 1, and that is a height at -2. At f at -3, here's an open dot, so that's not the height it wants. It wants this height right here, which is 5. And so those would be my function values at -5, 1, and -3. So you guys go ahead and try this one. So you can pause the video and try. All right. The limit at -3, the height of the graph at -3 is 3. So the limit there is 3 because on both sides it's approaching 3. The limit at -1, notice it's approaching two different heights at -1, so the limit there does not exist. At 0, it's approaching a height of 3 from both sides, so the limit is 3. At 1, from both sides, it's approaching a height of 2, so the limit is 2. At 3, from both sides, it's approaching a height of -2, so the limit is -2. F at -1, the actual function value, the closed circle, is at a height of 2. F at 1 does not exist because there is no closed circle at 1. And then F at 3 is this value right there, which is -2. All right. So left-hand and right-hand limits. Left-hand limits are what the graph is approaching as you're coming from the left-hand side, and right-hand limits are what the graph is approaching as you're coming from the right-hand side of the point. And so how we indicate that, right-hand limits have a little plus sign next to the number, and left-hand limits have a little negative sign next to the number. So on that first example, what is the value of the limit as x approaches -1? That little plus sign means from the right. So as you're approaching the graph from the right-hand side of -1. So on the right-hand side of -1 would mean as you're getting closer and closer to -1, coming from the right. So you're going to follow this little graph until you look at the height at -1, and the height at -1 coming from the right, it's at a height of +1. If we want the left-hand limit, so the one right next door, so with that little negative sign, this would be from the left. And so this would be the left-hand limit. Well, coming from the left side of -1, there's nothing there. The graph isn't connected on the left-hand side of -1, so that limit does not exist. All right, if we're approaching 1 from the right, so we're getting closer and closer to 1 coming this way, it would be this little piece of the graph. And as I'm getting closer and closer to 1, that height is getting closer and closer to a height of 1 as well. And then underneath that, that's approaching 1 from the left. So as I'm getting closer and closer to 1 on the x-axis from the left, so I'm coming this way, it's going to be this little piece that I'm following. And as I follow that piece, it's leveling up to a height of 2. And again, that's a hole, but that's okay. It can be a hole when we're talking about limits. It's what it's approaching, but it doesn't necessarily have to exist. And that would be 2. So what is the limit as I'm approaching 1 from the right? We already did. That was 1. What's the limit as I'm approaching 2 from the left? So here is 2, and that little negative sign means from the left. So on the left-hand side of 2, I'm coming this way. And so I'm going to follow this little piece, and that's going to be at a height of 1. And then if I want to do, let's change, well, nope, we can go up to here. And let's do 0 from the left. So if I want to approach 0 from the left-hand side, it would be coming this way. And so I'm following this piece down, and that would be at a height of 0. If I want to approach 0 from the right-hand side, that's coming this way. And so I would be following my graph down to 0 on the right, and it's approaching a height of 0 as well. What's my graph approaching on the right-hand side of 3? So I'm approaching 3 on the right-hand side, so I'm coming closer and closer to 3. Well, there's no graph on that side, so that limit does not exist. If I'm getting closer and closer to 3 on the left-hand side of 3, so I'm coming closer and closer to 3 coming this way, I'm going to follow this piece of the graph, and that's getting closer and closer and closer to a height of 1. So those are left-hand and right-hand limits. And then if I actually want to find the function value at 0 is 0, the function value at 1 is 1, and the function value at 2 is this little isolated point up there, which is 2. All right, you guys can go ahead and try these. You can pause the video and try. So as I'm approaching -3 from the right, it's going to be this point right here, which is at a height of 2. If I'm approaching -1 from the right, it's approaching this height right here, which is 3. If I'm approaching -1 from the left, it's going to be this little piece of the graph, and that's at a height of 0. If I'm approaching +1 from the right, it's going to be approaching this way, and so it's going to be that value, which is 1. If I'm approaching 1 from the left, then I'm coming this way, and again, it's still at a height of 1. If I'm approaching -3 from the left, I'm going to use this little piece of the graph, and that is approaching a height of 2.5. If I'm approaching 0 from the left, I'm going to use this piece, and that is going to be at 2. 0 from the right, I'm going to use the other piece, and that is also approaching 2. If I'm approaching 2 from the right-hand side, so I'm getting closer and closer to 2, I'm going to use this piece right here, and that is going to be at a height of -3. And then 2 from the left, or you're going to use this piece, and that's going to be at a height of 0. And then f at -1, it looks to be 1.5. It's going to be this dot right here. F at 1 is going to be this dot right here, which is at a height of 3. And f at 2 is that dot right there, which is at a height of 0. If you just want to find limits algebraically, your first step is just plug in the x value and see what happens. If you get a number without a restriction, like you don't get 0 in the denominator or a negative square root, then that's going to be the height of your graph. So the limit as x approaches 2 of x minus 2, if you plug in 2, 2 minus 2 is 0. Or graphically, x minus 2 is just a straight line with a y-intercept of -2, and it goes up 1 over 1. So if I graph that line, what's the height as I'm getting closer and closer to 2? Well, notice that height as I'm getting closer and closer to 2 is at a height of 0. What's the limit as x approaches 2 of x to the third minus 4x plus 5? Again, the first step is just plug in the x value and see what you get. So 2 to the third minus 4 times 2 plus 5 would be 8 minus 8 plus 5. And so that's just going to have a limit at 5. So again, your first step on any limit problem, if you need to find it algebraically, is just try and plug in the x value and see what happens. Some property of limits that we're going to go over today and again is that if you have two different functions, so let's say f of x is just x and g of x is x squared, and you want to find the limit as x approaches 1 of f of x plus g of x, well, you can literally just find the limit as x goes to 1 of f of x, and you can add that to x goes to 1, the limit as x goes to 1 of g of x. So you could find the limit as x goes to 1 of x, and the limit as x goes to 1 of x squared, and it would be the same thing if you found the limit as x goes to 1 of x plus x squared. So that's the sum. It also works the same way with differences. It also works the same way if you're multiplying, and it also works the same way if you're dividing. You can separate them into two separate limits if you want to. You can also have a constant. So if I had the limit as x goes to 1 of like 3 times f of x, you can take that constant, that coefficient, and pull it to the front. So that's the same thing as 3 times the limit as x goes to 1 of f of x. So those are just some properties of limits that we're going to talk more about throughout this unit. Evaluating limits using a table. So again, your first step on any limit problem is trying to plug it in. So if I try and plug in 2, then I would get 2 minus 2 over 2 squared minus 4, which ends up with 0 over 0. That's sad. That's called an indeterminate form. That means that the limit might still exist, so the height of the graph might be approaching a given number, but I can't tell right now just algebraically. So we can make a table. So if I made a table, I want to get super close to 2. So I want to know what's happening on both sides of 2. So I want to know what's happening at 1.99 or 1.9 or 2.01 or 2.001, because I know at 2, my graph is undefined, but I want to know what's happening as I'm getting really close to 2. So if I wanted to use a table and do this, I can go to Desmos, and Desmos can create a table for me. So if I go to Desmos, I'm going to type in, so I'm going to make one of my values, I'm going to type in the function, and if it's a fraction, make sure the numerator goes in parentheses, and then we're going to divide by x squared minus 4. So we're going to type that into Desmos, and I'm going to show you how to evaluate using a table. So if I go to Desmos, so since it's a fraction, I'm going to put my numerator in parentheses, so x minus 2, and then it's going to be divided by x squared minus 4. So this is a picture of the graph, and I wanted to know what's happening to my graph as x is getting closer and closer and closer to 2. So if I were to blow this up a little bit, it looks like it exists at 2, right? But if I were to bring this and go and swing this around and get to exactly 2, notice at 2, it's undefined. It doesn't exist at 2. So we want to see what's happening as I get really close to 2. So if you hit the little gear button above your function, that guy right there, notice you have paper and X, and then you have a little table guide. So we're going to put it in a 2. So notice at 2 right here, it's undefined. Well, I want to know what's happening at 2. So I'm going to go to 1, and then I'm going to hit the return key, which is the little blue arrow. And I want to get close to 2. So what if I was at 1.9? Well, it looks like it says 0.256. Well, let's even get closer to 2. So I'm going to hit return again and put 1.99999. Ooh, that looks like 0.25. What about on the other side of 2? So let's do 2.0000001. Ooh, that's 0.2499999. What if I got even closer? Let's see how I did 2.00. Oops, I didn't. In the wrong area. Go underneath. 2.000000000000001. Oh, we're too close to it. So it looks like on both sides of 2, if I get really, really close to 2, it looks like on both sides I'm getting closer and closer and closer to a height of 0.25. And that's what my limit's going to be. So I'm getting closer and closer and closer to a height of 0.25. And that's going to be my limit. Well, let's look at this problem again and see if there's another way we can think about it algebraically. When you are given this problem, what's one thing that you know that you could do to the denominator? You can factor it. Well, let's factor it and see what happens if we can cancel anything. So that would factor to x plus 2x minus 2. What could cancel in this problem? The x minus 2's could cancel. And what I'm going to be left with is the limit as x goes to 2 of, since everything canceled out of the numerator, it's a 1, and then over x plus 2. What happens if I go back to step 1 on evaluating limits? What happens if I plug in the 2? I get 1 over 2 plus 2, which is a fourth. And a fourth is the same thing as 0.25. So we actually can evaluate that limit algebraically, but we can also do it using a table on Desmos. So you guys go ahead and try this one. So put this into Desmos and see if you can tell me what the limit as x goes to 0 of cosine x minus 1 over x would be using your table on Desmos. You guys can check your answer against the finished notes from class today. All right, so evaluating limits algebraically, steps that you can take. So if you want to evaluate limits algebraically, some steps you can take. Step 1 is you're going to plug in the x value and see if it works. If you get a value that works and it's not undefined or indeterminate, you're good to go. If that didn't work, then step 2, you're going to try and factor and cancel if possible. You're going to try and get a common denominator if that's helpful. You're going to try multiplying by conjugates if that's possible. You've got some options. So we're going to talk about those different options if they exist. And then after you do that, you're going to try to plug in the x value again. So if one of those things from step 2 work, then you're going to try and plug in the x value again and see what happens. So try to plug in. That's step 1. So let's look at the first one. So it's telling you to plug in 2 pi over 3. So as r is getting closer to 2 pi over 3, what's this limit going to be? Well, it's going to be negative 2 times the cosine of 2 times 2 pi over 3. And so this is going to be negative 2 times the cosine of 4 pi over 3. And the cosine at 4 pi over 3, well, 4 pi over 3 is going to be down in the third quadrant, and all students take calculus, so it's going to be negative a half. So this is going to be negative 2 times negative a half, which is positive 1. So that limit's going to be 1. Let's look at the one next door. What's the limit as x is getting closer and closer to negative 1? So if I plug in negative 1, that'd be negative 1 plus 4 over 1 minus 14 plus 49, which would be 3 over negative 13 plus 49 would be 36. So this would be 1/12. All right, you guys try the bottom two, and then you can check your work against the finished notes from class today. So I told you sometimes when you try and plug in that it won't work, and then you might have to factor and simplify. Well, the first step is always try and plug in first. So if I plug in 3 into the numerator, I get 9 minus 9, and if I plug 3 into the denominator, I'd get 9 minus 9, so I'd get 0 over 0. So again, that's called an indeterminate form. So if you get an indeterminate form, we're going to try something else. So in this case, see if you can factor. We can factor the numerator. It would factor into x plus 3 times x minus 3, and the denominator is x minus 3. And then notice the x minus 3's can cancel. At this point, you try and plug in again. So if I take 3 and plug it in, 3 plus 3 is 6. So the limit as x goes to 3 is going to be 6. All right, if we try the next one, if I plug in 2, I would get 4 minus 14 plus 10, which would give me 0. And if I plug 2 into the denominator, 2 minus 2, that would give me 0. So I would end up with 0 over 0. That's an indeterminate form. So I can't tell what the limit is. So let's try and factor. So the limit is x goes to 2. And this would be x minus 5, x minus 2 over x minus 2. And again, the x minus 2's will cancel. And if I try and plug in the 2 again, 2 minus 5, the limit is going to be negative 3. So that graph will be approaching a height of negative 3 when the x values get closer and closer to 2. All right, you guys try these 3 limits, and you can check your work against the finished notes from class today. Another option when evaluating limits is if it's a complex fraction like this, sometimes you're going to want to get a common denominator. So again, first step, plug in x, the value for x. So this would be 1 over 2 plus 0 minus a half over 0, which would be 0 over 0. That's an indeterminate form. So now we're going to try and get a common denominator. So the common denominator here is going to be 2 times 2 plus x. So I'm going to multiply the second fraction by 2 plus x, and I'm going to multiply the first fraction by 2. So this is going to be the limit as x goes to 0, and that's how I'm going to change the numerator, and the denominator is going to stay x. And so if I simplify this, I would get the limit as x goes to 0 of 2, and then I'm going to distribute that -1 minus 2 minus x all over 2 times 2 plus x, and then all over x. And if I simplify that, I would get the limit as x goes to 0. 2 minus 2 is 0, so I would get -x over 4 plus 2x. I just distributed here, and then all over x. Well, I have a fraction divided by a fraction, so this would be -x over 4 plus 2x divided by x. What happens when you divide and you have fractions? Well, you're going to multiply by the reciprocal, and the reciprocal of x is 1 over x. So this is going to be -x over 4 plus 2x times 1 over x. Well, what happens to those x's? They're going to cancel. So now this is going to become the limit as x goes to 0 of -1 over 4 plus 2x. Well, what happens if I plug in 0 now? I get -1/4. And we could check that if we were to plug that into Desmos and use a table, then that expression should get closer and closer to -0.25 as my x values are getting closer and closer to 0. So the common denominator is another option when trying to figure out limits. And then I told you might also need to multiply by a conjugate. So the first step, plug in. If I plug in -10, I would get the square root of 9 minus 3 over 0, which would be 0 over 0. So that's an indeterminate form. So the conjugate of x plus 19, the square root of that, minus 3, its conjugate is going to be the square root of x plus 19 plus 3. So I'm going to multiply the numerator and denominator by the conjugate. So basically, I'm going to multiply by 1. So I have x plus 19 minus 3, and I'm going to multiply that by its conjugate, the square root of x plus 19 plus 3. But whatever I do to the numerator of a fraction, I've got to do to the denominator. So the denominator was x plus 10, and I'm going to multiply that by the square root of x plus 19 plus 3. I'm not actually going to multiply out the denominator. I'm just going to FOIL out the numerator. So if I took the square root of x plus 19 times the square root of x plus 19, I'm just going to get x plus 19. And then if I took the square root of x plus 19 times 3, then I would have positive 3 of them. And if I took -3 times the square root of x plus 19, I'd have -3 of the same thing. Those are going to end up canceling each other out. And then if I distributed -3 times positive 3, I would get -9. And then I'm going to keep the denominator. I'm not going to FOIL it out, so I'm going to leave it as x plus 10 times the square root of x plus 19 plus 3. Now notice what happens. My numerator, and I'm sorry, we can't drop our limit, so it's the limit as x goes to -10 of this. My numerator is going to be x plus 10. But notice what happens now. My x plus 10 in the numerator and the x plus 10 in the denominator are going to cancel. And so the only thing that I'm going to be left with is the square root of x plus 19 plus 3 in the denominator. So now I have the limit as x goes to -10 of 1 over the square root of x plus 19 plus 3. So now if I plug in -10, I get 1 over the square root of 9 plus 3, which is going to be 1/6. So multiplying by a conjugate is another option when you're taking square roots, or taking limits, sorry, of terms with square roots. So you guys go ahead and try this one, and then you can check your answer against the finish notes from class today. Using a graph or a table to check. So if I wanted to take the limit as h goes to 0 of the square root of 4 plus h minus 2 over h, well, if I plugged in 0, I'd get the square root of 4 minus 2 over 0, which is 0 over 0. So we're going to use the conjugate approach. So the limit as h goes to 0 of the square root of 4 plus h minus 2, and then its conjugate would be the square root of 4 plus h plus 2. So I'm going to multiply the numerator and the denominator by the conjugate, the square root of 4 plus h plus 2. If I FOIL out the numerator, I would get the limit as h goes to 0 of 4 plus h, and then the middle terms will go away, and then minus 4 over h times the square root of 4 plus h plus 2. And then notice the 4's will cancel, because positive 4 and negative 4 will cancel. So this will be the limit as h goes to 0 of h over h times the square root of 4 plus h plus 2. And now those h's cancel. So I'm left with the limit as h goes to 0 of 1 over the square root of 4 plus h plus 2. And if I plug in 0, this would be 1 over the square root of 4 plus 2, which is 1/4, which is 0.25. So I can check this. This is asking what's the height of the graph getting closer and closer to as my h values or my x values are getting closer and closer to 0. So I'm going to graph this on Desmos, the square root of 4 plus x minus 2 over x. So let's cancel this guy out. And we're going to do the square root, so it's a fraction, so the square root of 4 plus x, and then minus 2, and then divided by x. I believe that's what it was. And we want to know what's happening as it's getting closer and closer to 2. So as I'm getting closer and closer to 2, nope, this should be minus x, shouldn't it? I feel like I typed that in wrong. Oops, let's go back to the notes. The notes said 4 plus x minus 2 over x. Oh, as I'm getting closer and closer to 0, that's what I wanted. So as I'm getting closer and closer to 0, what's happening? So as I'm getting closer and closer, so at 0, remember, it's undefined. So as I'm getting closer and closer to 0, what's happening? Well, like if I just follow this dot, as I'm getting closer and closer to 0, it looks like it's getting closer and closer and closer and closer and closer to the y value. Looks like 0.252, 251, 251, 251. And then if I'm 0.25, if I'm getting closer and closer and closer, my y values looks like 0.246, 0.247, 0.248, 0.249, there we go. So it looks like they're getting closer and closer and closer to a value of 0.25, which is what we had. Or if we go to our table, we want to know what's happening as I'm getting closer and closer and closer to 0. So negative 0.00001. Look, it's really, really close to 0.25. And if I'm bigger than 0, so 0.00001, again, those look like they're getting closer and closer and closer to 0.25. So it looks like graphically on the table, we did it algebraically correctly. All right, so gentlemen, your homework is from